Okay, welcome to the last video of this section. We're going to actually look at an example and show not only how to approximate it like you still are doing in section 2, but actually how to take a limit and find the actual area under the curve. And as my guinea pig, I decided to mess around with this particular parabola, okay? You may or may not remember how this guy graphs, but if you do, so much the better. Basically, you can tell that the vertex is, say, looking at the numbers in there. I don't know if you remember this, 2 comma 1. So not that this is important to the problem, but graphing skills always are a good thing. And what we're going to do is we're going to approximate the area under this guy. Let's see, where is he now? He's here, and then this guy's way up here, something like that. Okay? And this guy is saying, this problem is saying, let's figure out the area under the curve. Let's see, over this interval 1 to 4, and we'll use n equals 6 subintervals to do it. So what we're going to do is look at the interval. We're actually starting at 1, and we're going way out here, say this is 4, and we're going to try to contrive to figure out the area under that curve. Okay. All right, first we're going to estimate it with n equals 6 subintervals. Okay, so the way that goes is you take that number line, which goes from 1 to 4. If you're in a hurry, you might go something like this. Well, delta x is b minus a over n. So for us, it's 4 minus 1 over 6, which looks like it is 1/2, or how about 0.5? So that means when you're, and you could have figured it out by just looking here, but basically we are cutting this into, what am I doing? Let me get rid of my marks there. I got to cut it in pieces, in 6 pieces, right? So we cut that into, and then that, and that, and that, and that, okay? So 1, 2, 3, and 4 are here, right? And 1 is here. And our guys are the intervals that we're going to use. Let's use the right endpoint, okay? So for each interval, we'll use the right endpoint. So 1.5, 2, 2.5, and there he goes, 2.5, 3, and 3.5, and then 4. And if you remember how this is done, you can be pretty quick about it. You can say, and I'll say it this way, watch this. The area under the curve, I'm now going to say, is the integral, the definite integral from 1 to 4 of this function. What function? Oh, if I'm going to be fancy, okay. What I have to do is maybe write this in terms of as a function. So you'll verify that when I multiply this stuff out and gather everything on the right, we have x squared minus 4x, and I believe it's plus 5. So yeah, that's where we're integrating, so to speak. X squared minus 4x plus 5 dx is approximately, okay, you ready? It's approximately 0.5 outside. And then in this function, we're going to plug in all of those 6 points. So it's going to be, and I'm not going to write them all out because I think you know what I'm talking about. You're going to take the first number and square it minus that number times 4 plus 5. That's the first guy. You go to the next guy, and it's going to be, maybe I better use some brackets here or something. It's going to be squared again, minus 4 times it, plus 5. Okay, so the numbers are, let's see, what are the numbers? It's going to be 1.5 here. Then the next one is 2. And if you've done your homework, you know what I'm talking about. Plus, there are 4 more, and the very last one I'm going to fit down here. I'm going to say, plus the last one is when you plug in the number 4, right? So it's going to be this guy squared minus 4 times this guy plus 5, bracket, bracket. And so that's the last number, and it's 4, okay? So you whip out the calculator, and you come up with your approximation. I already did it. I'm looking for the number now on my piece of paper. I think it's 6.875. 6.875. And that's an estimate of this area under the curve. Now I'm going to show you how to do it by taking the limit, okay? And this is going to be, well, as we used to say in surfing jargon, pretty gnarly. You ready? Okay, so that's my estimate with n equals 6 subintervals. It's not that fast because you have to use your calculator. what we're going to do is do the same problem, and we're going to use the definition of the definite integral to calculate the exact area this time, which seems miraculous. Well, after we're done, you're going to say, no miracle, it was just blood, sweat, and tears. But it's not that horribly horrible. So it's the same thing. We're estimating, actually we're going to go after this guy. So it's x squared minus 4x plus 5 dx. Okay, we're going to use the limit definition. Okay, so we're going to say, hey man, it's the lim as n goes to infinity, and we're going to add up all those rectangles, from I equals 1 to 6. No, we're going to go past 6. We're going to go as far as we want because we're going to plug in this function. Now here's the thing. My function, I have to plug in the right numbers, and when I'm done, I have to multiply it by the correct delta x also. So we have a little backtracking to do. You ready? We have a little bit of groundwork. So our integral is from 1 to 4, granted. And what we're going to do is we're going to split this guy up into n subintervals of the same length as we go around through this, okay? Pretend they're all the same length, okay? So we did this on a previous lecture, but we're going to do it again. First of all, we'll find the delta, okay? So if that's our first work here. We got to go delta x is b minus a over n. For us, it's 4 minus 1 over n, because I don't know what n is. And so our delta this time is 3 over n. Okay, so I'll put that up here, times 3 over n this time, because n can be anything. And of course, when we take the limit, n's going to get bigger and bigger and bigger. Okay, but we're not done. The next part of this is if we use the right endpoints method, okay, then I'll put this in red so you can see it better. Then what we're going to do is we're going to use each one of these right endpoints all the way to the end. Starting at 1, the first one is, ready? Oh boy, this is going to be fun. It's going to be 1 plus your delta, which is 3 over n. So you're going to go, here's 1, and we're going to add 3 over n, and that's where we are now, right there. If we add 3 over n again, we're at the next one, so that's going to be 1 plus 3 over n times 2. And you go all the way through. The generic formula, I don't know where you are, but it's going to be 1 plus 3 over n times I. And I is going to circle in this summation. It's going to circle through 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, all the way to whatever number you want. Okay? That guy, this formula right here is what's going to go in for all of them in your sigma notation. That's the beauty of the sigma notation, the summation notation, is it's a shortcut for add these guys and this is how the terms change. Well, the terms change because you're jumping from this guy to this guy to dot, 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 this guy, dot, 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 all the way to the end. Okay? And so we're going to plug that into the function. And what the function does is it takes things and squares it, and then takes minus 4 times it, and then plus 5. And guess what, man? This is what we're going to do. We're going to plug in 1 plus 3 over n times I. 1 plus 3 over n times I. And that's the start of the game. I'm not saying it's easy, but that's how you start this thing. Pretty crazy, right? You have to, and this is why this is difficult. We're not comfortable with summation notation yet. We're just not, okay? But every time I think about it, think of it as a string of numbers, and you can do things to these guys. All you really have to do at this point, though, watch this, is multiply all this stuff out. So it's still the lim. As n goes to infinity, it's going to be summation. I is 1 to n. But here comes some fun. We're actually, I'm going to make this big old bracket. We're going to actually FOIL out this thing. We're going to, do the FOIL on it, right? Square a binomial. We're going to get 1 plus 2 times, I'll write it, 2 times 3 over n, and then plus I forgot the I, and then plus, we're going to square it, so plus 9 over n squared I squared. 9 over n squared I squared. It's fun. We're going to distribute the 4. We're going to get a minus 4 minus 12 over ni and then plus 5. And who's waiting outside? 3 over n is still waiting. Okay, so all this is really just messing around with this thing right now. It's nothing but algebra. I know you don't know what's going to happen. There's a trick at the end. You're going to find out what it is in a little while. So I'm going to distribute this guy. Well, no, I'm going to collect like terms, and I'll do that first. I don't like to get confused. So let's see what we got. We got, for numbers, we've got 1 minus 4 plus 5. Sounds like, I think, a 2, is it not? Yeah. So we have a 2 there. Okay. Let's see. If you gather this and simplify it, you can see how fun this is. I got to a point where I ended up writing this. Okay. I had 9 over n squared I squared. And then I had minus 6 over ni, and then plus 2, and then waiting outside is still that delta, 3 over n. And when you bring that in and distribute it, n is going to infinity. We've got summation I equals 1 to n. You end up with, I think, let's see, 27 n cubed I squared. Is that right? We have 27 over n cubed. Let me check my work. 27 over n cubed, that is correct. I squared still. And then we have minus 18 over n squared and then an I. And then finally plus 6 over n. Is that right? You liking that? I said, are you liking that? Not really. Okay, so now here's the fun part. Remember that stuff where you can split the integral into 2 pieces if you want to, like you got a sum or a difference? I'm going to do that right now. I'm going to do it right now. I'm going to say lim, n goes to infinity. I'm going to treat each of these terms separately. Watch what I write. I'm going to go big old bracket this time. I'm going to write, okay, n is going to infinity, correct? So, but in this guy here, this is going to be really strange to you guys, but what's happening here is I is the guy that's changing, and it's going to go through 1 squared, 2 squared, 3 squared, 4 squared. So what the author tends to do, well, I'm not going to do it that way. I'll tell you why. That's a little too confusing. All right, I equals 1 to n, and I'll keep the 27 over n cubed inside times I squared. Okay, I'm going to come back to that. Okay, and then I'll say minus in sum I equals 1 to n, and there's a reason to do this, and I hope it makes sense to you that that happens. And then finally plus summation I equals 1 to n, and this is 6 over n, like that. So what? So here's the thing. What you need is a little bit of a crash course again on these summations. So I'm going to put here, I'm going to put this in a little region like this is a thought bubble or something. What's happening on the first one, without taking the limit, is the following. What you've got is each one of them has a multiplier 27 over n cubed. But what happens is the first one is 1. See, the counter starts at 1 and it goes 1 squared. And then the next one is 2 squared. Okay? And the next one is 3 squared, and then you go all the way out to n squared. And notice I didn't write the 27 over n cubed next to that, I just wrote it factored out. And I'll do the same thing here, minus 18 over n squared, and then this time it's 1 plus 2 plus 3 plus dot 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 plus n. Okay? And then lastly we've got plus, I'll factor out 6 over n, and really this is 1 plus 1 plus 1 plus 1, and there it's n times. See, this counter is saying I equals 1 to n, and there is no I. So it's really just 6 over n plus 6 over n plus 6 over n times. Okay? That's going to help you understand what we're about to do. Okay? So I will now turn your attention to a little bit of pre-calculus talk. And this is found, let's see, it's found on page 381. So you'll see, refer to page 381 at this moment. And so this is what we're going to get. We're going to get lim as n goes to infinity. and a big old bracket, and we're going to get this guy. I'm going to replace this with 27 over n cubed. Where'd the sigma go? Well, the sigma is lost because I wrote it out instead. Okay, so I don't need the sigma to tell me. But here's the thing. On page 381, we have a formula for the first n squares being added. And you're going to find it on page 381. The formula is n plus 1, 2n plus 1 over 6. N times n plus 1 times 2n plus 1 all over 6. It's a closed form for the sums of the squares. And some of you might go, oh, murmur, I think I remember some. If you don't remember that one, you might remember this one better. This one is n plus 1 over 2. The sum of the first n integers. This is pre-calculus stuff we forgot. And the last one's fun too. It's 6 over n. And if you've got n ones, guess what that's equal to? N. I didn't give you a chance, huh? So let's see what our limit is. The sigma is gone, baby. It got replaced by this summation formula, what they call a closed form. So we have lim as n goes to infinity of. Okay, we're going to take these limits now one at a time, okay? Upstairs we have, if you were to multiply upstairs, it would be 54. Do you see the 2? Do you see the 27? I'm going 54 times n cubed plus I don't care what else. And downstairs is 6n cubed. Okay, I'm going to look at that first one. Remember, n is going to infinity. So since the powers match, do you remember this jive? You go to 54 over 6. You want to play the game yourself on the next one? Okay, in the next one, it would be like 18 n squared, and you can actually do it. It's like, what is that? Plus 18n, right? Okay, and downstairs is 2n. Where'd my n go? I lost it. There he is, 2n squared. I forgot the square there. So it's 2n squared here. So we play this game, we go, aha. So that limit is equal to, it's going to be minus 18 over 2. And lastly, this guy, just cancel the n's. And you've got plus 6. Okay, you know what this is? This is 9 minus 9 plus 6, and the answer is 6. Ladies and gentlemen, I verified that with skills that we're going to learn in section 3. Way faster way of finding the end result, and the answer is 6. The area under this guy, way back here, is not 6.85. That's a little too much of an estimate. In fact, if you look at the rectangles, a little bit of it starts becoming a much bigger overestimate of the answer as you go. So he's a little too large, isn't he? With more rectangles, you get closer and closer to the truth. And the truth is, where are you? Right there. Okay, so that's an example. I've given you a couple to play around with to do, see if you can come up with it. What saves our bacon? 2 things. I understand sigma notation and breaking it apart. If ever you get lost, when in doubt, write out the terms and see if you can get unlost. And then, of course, then we have to lean on that formula, those formulas. And that's it for section 2. It's a big one. Thanks for listening.